So we are going to look at carbon in the section on substances. We just finished nitrogen. We will look at carbon present, past and present here, and then in the next section we'll look at carbon present and future. But here it's in the context of geoengineering and how we have changed the carbon cycle, just like we looked at the nitrogen cycle. I have a course called Global Carbon Cycle, which is based on David Archer's primer on the carbon cycle, where we look at past, present, and future carbon cycles, but from a perspective of climate change and feedbacks at different time scales and whether carbon cycle is stable or unstable and so on. Here we will start by looking at carbon cycle in the context of energy, and then transition to how humans evolved, climate evolved, and carbon has evolved, and how we are perturbing the carbon cycle at present and how it has evolved in the past. Starting with this quote from Peter Westbrook's book Life as a Geological Force from 1991. As an 8-year-old boy, I walked through the dunes with my father. Look around you, he said. All you can see is really there. Yet, behind each thing lies a mystery, hidden from view. If you try hard, you may get a glimpse of that world, but never will you be able to see it all. So it's basically talking about looking at nature and looking at indicators running back and forth in time, and what may be obvious and gets our attention, and what we may miss if we don't pay enough attention. The book starts with a discussion on radiation by Soddy and Rutherford, and talks about nuclear energy and potential scale of human energy generation, going from just a 0.2 exajoules to now I don't know how many exajoules and so on. But we can look at this figure from our world in data, looking at global primary energy consumption by source, where each of these are converted by using a substitution method into a scale that can be combined to show as in terawatt hours. The details don't really matter, but before the Industrial Revolution, before electricity and so on, fire has always been mastered by human beings, so it came down to biomass and animal oils and so on for making fire and light and heat. Over this period, the biomass has not disappeared. It's still there very much. But coal has evolved over time and drove the Industrial Revolution in the beginning, and now we want to get rid of it as soon as possible. But as I showed in the last section, many countries are still to get rid of it. Oil evolved along the way, gas, and then of course nuclear, hydropower, wind, solar, and other modern biofuels and renewables like geothermal, etc. So the idea is that these predominant sources are now carbon-based sources, and obviously we are talking about geoengineering because we want to remove the carbon or remove the impacts of carbon, right? So carbon has always been part of life, part of humanity. Life is carbon. If we look at electricity generation, US is rich and is way up here compared to other countries. There are many in the middle, but we jump to India, which is growing because it wants to provide electricity to the hundreds of millions of people who don't still have electricity at home. That is France, United Kingdom, and Sweden. And again, this is closely related to GDP, carbon intensity of energy production, and energy intensity of GDP, and so on. So it still comes down to that. Looking at the perturbations and past carbon cycles, let's start with just pre-industrial time scale. So we are looking here at fluxes in gigatons of CO2 per year. The green numbers are the pre-industrial numbers, and the recent changes made are shown in these red arrows. And the CO2 levels at South Pole from 1958 to 2004 are shown here, going from 315 ppm through 375. Obviously we have now blown past 420 or so. So the main message is that before the industrial age, sources of CO2 were nearly balanced by sinks, even though we will see that Bill Ruddiman claims that human impacts are visible from 10,000 years ago, when we started doing large-scale agriculture, settled down, grew in population, started demanding more food, fertility rates went up, and so on and so forth. So Overall respiration would have been about 450 gigatons CO2 per year, with photosynthesis balancing all of that globally. And the ocean, this is for the land, ocean would be releasing 260 but absorbing 260 as well. But now we are emitting by industrial activities 26 gigatons. Changing land use is a contribution of 6 gigatons per year. Volcanic activity is putting in about 0.3 from the pre-industrial estimation, and weathering would have been taking about 0.7, which are estimates. With global warming, weathering rates should go up because warmer temperatures favor faster weathering rates. Nonetheless, the planet is now is taking up about 15 additional, as we will see in a minute, because as we increase the CO2 in the atmosphere, plants, land use, the vegetation takes it up, ocean takes it up. So ocean is releasing 70 and absorbing 80, so 10 is the additional number there. And in the atmosphere, we are accumulating about 15 gigatons per year. We will look at other variations of these numbers, but essentially the idea is that we have gone from a system that was nearly balanced in terms of sources and sinks, in terms of carbon cycle globally, to a system that is now accumulating in the atmosphere. There is definitely some accumulation happening on land, and there is penetration of invasion of anthropogenic carbon into the ocean, right? So we are putting carbon away in different systems. You can look at the contribution of fossil fuel burning by looking at what is called negative isotope excursion. So the delta C 13O2 in parts per mil or parts per thousand, going from about the middle of the medieval warm period 1,000 years ago or 1,000 years AD. This is data from Laudon and Cape Grim. When you burn old fossil fuel, which is photosynthesized hydrocarbon, remember photosynthesis fractionates carbon and prefers to take up more 12 CO2 because that's lighter. So old hydrocarbon is depleted in C13, so when you burn it, you're going to put more of that into the atmosphere, and that shows up clearly here as a significant negative excursion. And past negative excursions are also used to interpret climate carbon interactions and so on. Tricky business, but nonetheless. So this shows the same thing, but now going back 10,000 years ago, you had reaction with calcium carbonate on those time scales coming out of the glacial conditions, and temperatures begin to warm, atmospheric CO2 begins to increase naturally from the ice age low of about 180 to 200 ppm to 280 ppm or so. Here we are talking about it in petagrams carbon. So that would drive pH changes, calcium carbonate reactions, and reactions with igneous rocks and so on. But over the recent 2,000 years, if we look especially over the last 200 years of industrial revolution, ocean and land are taking up more of the carbon because of these things we talked about, right? Carbon gets taken up by various sinks as we keep pumping it into the atmosphere. So you can put it in the context of the Keeling diagram we've been looking at, collected since the 50s, which is now at 417 in this figure, but we have gone to about 420, I think, and it's combined with ice core data on pre-industrial levels, so 278 ppm by the beginning of the industrial revolution. So this is what we are doing. This is, of course, can be put in the context of very long time geologic time scale variations in carbon dioxide, estimated with various evidences from stomata, liverworts, paleosols, alkinones, forams, and so on. Paleosols are old soils. Antarctic ice core data more recently, and so on. Obviously, CO2 has been very high in the atmosphere before, but obviously we were not around, and these were natural variabilities. But the point is, CO2 has always been part of climate variability, and life has always played a role along the way in terms of photosynthesis, drawing down CO2, respiration, releasing it. This is why you have evidences in forams and alkenones and so on. And we came out of the ice age, and we were somewhere here through the Holocene, and then we've been increasing it here, and into the future, if we continue business as usual, we're going to end up with levels that we haven't seen for many tens of millions of years. So the planet doesn't care, and many life forms will survive, but our survival is at question. And then we have other scenarios which we consider in terms of renewable energies, population growth, policies, bioenergy and carbon capture and sequestration, direct air capture, and so on, to try to hit our global warming targets. Okay, so this is the context for past carbon and present carbon and where we are headed into the future. But we will now go and see how the radiation forcing also has changed over this period, and how human evolution has interacted with climate as well, so that we can carry carbon, climate, and humans together before getting back to geoengineering, which is our main goal here. Okay, so we'll come back and look at further details on the carbon cycle, climate change, and human evolution.